Hi, my name is Jared Ely, and this is my presentation on an active learning methodology applied to two lessons on reaction kinetics. These lessons are geared towards an AP level chemistry classroom, but could very well be adapted for use at an honors level. Overall, this presentation will proceed through some details of the lesson plans, along with the prerequisite skills and common misconceptions that go along with reaction kinetics. Following this, I will briefly describe the active learning method for this topic, the 5E instructional model, followed by another classroom technique I like to use in my class, mastery style learning. Finally, I will go through a quick summary of two lessons on reaction kinetics, followed by a listing of the resources for this presentation and the literature references used. First, let's go through the details of the lessons. These two lessons will focus on the early skills involving rate laws, including how to construct simple rate laws, which relate the reaction stoichiometry to the rate of change for each species in that reaction. We'll then proceed through differential rate laws, as well as the graphs of integrated rate laws. Following these early lessons, a full unit on reaction kinetics would naturally proceed through the effects of temperature, surface area, and catalyst action on reaction rates, but these two lessons are just going to focus on those early skills. Some of the prerequisite skills students would need for these lessons are first, a grasp of stoichiometry in terms of both what it means as well as how to balance simple chemical equations. They would need to know how to calculate concentration and also how to calculate simple rates. Finally, students would need some math skills as far as graphing simple relationships, as well as how to use logarithms. Some of the common misconceptions that students may have regarding reaction kinetics, especially after learning about them for the first time, were identified by Marzabal et al. And are displayed below, along with a suggested reaction that could address each misconception, as well as explore the topic a little bit further. First, they found that students commonly assume that concentration and reaction rate always have a linear relationship, regardless of what the reaction order actually is. Another very common misconception was that the stoichiometry coefficients from the balanced chemical equation are equal to the exponents in the differential rate law. This is especially pernicious and especially present because we do use those stoichiometric coefficients when developing our early rate laws, when we relate the different species to one another, as well as to the overall reaction rate. Two other misconceptions they noticed were one, that some students thought that temperature only increases the rate when you have an endothermic reaction, similar to how the equilibrium shifts according to Le Chatelier's principle, and also neglecting the presence of an intermediate species, basically treating every reaction as an elementary reaction. As mentioned, Marzabal et al. Did provide a number of reactions that could address these specific misconceptions, and they are listed below. Not all of these are going to be super appropriate at a high school level. The first one certainly is, and the second one could be done, but they all could be done at an early college level. Through these two lessons, a few different activities and technologies will be used as part of the active learning strategy. The first of these activities are Nearpods to both open the lesson as well as potentially close them. I don't have them as that, but they can be used as such. I personally find that using short Nearpods as warm-ups is extremely valuable, as I can see the entire class's responses as the students work. I can see all those responses at once, kind of walk around the room and address any misconceptions on a student by student basis, as well as bring everyone back together and show the class kind of how they responded and how we might change those responses, or if there's any kind of large scale class wide errors. Next, we do use Vernier software and Vernier LabQuest devices in lab. These are very, very helpful for using very simple sensors throughout our reactions. We're especially going to use the gas pressure sensor in this. They work great. There's some Bluetooth options available. They sync with students' Chromebooks, and they're great for getting simple data and analyzing it graphically. That being said, we do end the lessons, at least these two specific lessons, with a Google Form exit ticket. I like to use these exit tickets as a way to both bring the class together at the end of the day. Very good for just logistics for ending the class, but it does give both the students a way to self evaluate, as well as myself, some formative assessment data that I can look at during class and afterwards. This very minor grade does incentivize students to participate at the end of class, and I personally accept revisions on these because I want students to see their misconceptions and act on them. Honestly, it's a great end of class procedure, and it gives me great data at the end of the day. We also perform two short lab explorations in this. I'll go through these when we actually get to the lessons, and two worksheets. All of these are taken from online sources that are listed at the end of the presentation. This next section will detail the active learning technique that I selected, along with a research-based teaching methodology that I've adopted in my classroom. The active learning technique I will be using for this module is the 5E instructional model. In a 5E model lesson, students will be led through a series of different stages that promote inquiry and student-directed learning. These stages consist of the following. First, we engage the students with some relevant phenomenon or question. We then let those students explore the topic with accessible activities and scaffolded assistance where the students really are leading their learning. Next, we get students to explain the concept to one another while the teacher guides the students towards a common understanding. Next, students will elaborate on that understanding through additional activities or work. And finally, both the students and the teacher evaluate what learning was accomplished throughout the class. This method has been used for over 3 decades, and it's backed up by a lot of research, including Grau et al., who showed evidence that this model was effective both in the short term for addressing misconceptions as well as the long term. One other methodology I use in my classroom is mastery style learning, a student centered practice that prioritizes student progress and rapid individualized feedback to encourage student growth and self reflection. While this method can take many forms, in my class I provide work revisions and regular formative assessments that are designed to give automatic feedback, and they're meant to be retaken. Essentially, my students perform these quizzes pretty regularly. They check over their work and they check my feedback as well. They use materials to educate themselves on these topics, and I provide these in a range of different formats. And then the students will retake the quiz once they are more confident with their abilities. There are multiple benefits to using this mastery style learning, but the basics are that the students can access the material at their pace using different means, and they're encouraged to fully participate and understand a topic before moving on to the next one. There are many, many reviews and research papers supporting the use of this mastery style learning. The reference paper by Wingett and Persky is a nice primer on how to implement this at the post-secondary level, although many of the ideas in this paper, they could be easily used at the high school level without any real modifications. During this next section, I will briefly talk through my first lesson as if I were describing the plan of action to my students. This will be followed by a breakdown of the lesson as it relates to the 5E model. I'll then show the second lesson in a much similar manner. All right, class, today we are going to try to answer the question, what factors can change the speed of a reaction? I will start with a quick demo involving the oxidation of iron, which we will then discuss class-wide through our Nearpod. Next, you will assemble in your lab groups to explore the decomposition reaction of hydrogen peroxide into hydrogen and oxygen gas, as shown on the screen, gathering your data as in the lab handout. As soon as you finish that lab, you and your group will come on back up and watch the kinetics lesson number 1 video, and then discuss with your lab group, which will follow up with a class-wide discussion on that topic, on those early kinetics. And we'll also talk a little bit about rate equations and how we can use them with your lab data. Per usual, you will then go to the practice for this section. That is the kinetics lesson number 1 practice linked on the screen. And at the very end of class, we'll come back together for an exit ticket to see what we learned. Now, the way this lesson is broken down exactly corresponds to the 5E model. Each activity proceeds in the 5E order. First, the audience is engaged or hooked by seeing how the rust, or oxidation in general, is formed by lighting steel wool on fire. The students are led through the idea that rust takes a relatively long time to form normally, and they've seen it before in their lives in some way. Given that they're high schoolers, a lot of them have dealt with rusty cars in some way at this point, or at least they've seen that. And this is modeled by lighting a piece of steel wool on fire in a normal atmosphere. You could do it on a fume hood. It's pretty safe in the classroom as well. And this is a visually arresting phenomenon, but it's pretty simple. It's also very slow, relatively speaking. But next, you put a piece of steel wool in an Erlenmeyer flask filled with oxygen, which you could get. They sell it pretty readily at, say, like a hardware store, or if you have canned oxygen, or you could also use a reaction to generate it, such as the decomposition of hydrogen peroxide, which is what the students are about to do. And then you light it again, and that steel wool is much, much more quickly oxidized in that oxygenated environment. So it gives the students that idea that if we have more of one of the reactants, because they see you fill it with oxygen, you might be able to accelerate that reaction. Next, the students will explore the topics themselves with a simple yet demonstrable lab that shows that higher concentrations of the reactants, hydrogen peroxide in this case, will increase the rate of the reaction. This lab is structured in such a way that the students will have to work together and interpret the results with each other's help, while the teacher intervenes only to address group-wide misconceptions. The idea is the students will hopefully come to those misconceptions themselves and amongst their own discussions kind of resolve them. But following this, the students watch a self-paced video based on the content and skills relevant for the lesson. Normally, I would try to make these videos, but honestly, there already exists a bunch of fantastic chemistry teachers on YouTube, and the one I've linked here does a pretty good job with this early rate law. And that being said, we then follow that video with a teacher mediated, not necessarily teacher led, but teacher mediated discussion addressing those common pitfalls and misconceptions about the topic. Afterwards, students work in their small groups on a practice worksheet where they take the skills they've learned now and just apply them to the theoretical scenarios. Finally, at the end of class, we all come back together and evaluate ourselves with that exit ticket before the period ends. These are brief screenshots of how my warm-up Nearpod is structured, as well as the exit ticket for the end of class. The Nearpod allows students to write their responses while the teacher monitors all those student screens from their kind of like controller screen. They can send out student responses either individually or give feedback individually. They can also use these for group-wide discussions. They can push out certain responses to the entire class and then have the class talk about them. The exit ticket is very straightforward. It's a simple 1 to 2 question quiz the class will discuss before the period ends. I typically use our built-in learning management system, Schoology, for this, but Google Forms can be used in very much the same manner. They actually do a very good job with aggregating the data at the end. Now I move on to the second lesson, which is organized in much the same way as the first, according to the 5E model. Class, today we will answer the question, how can we mathematically model those reaction rates we explored last time? I'm going to perform a classic reaction up front of the iodine clock using 2 solutions with 2 different concentrations, similar to what all you did during our last class, and we should see different results. After discussing how you might model that reaction using some simple math all through our Nearpod warm-up, you will once again assemble into your lab groups to perform the same reaction over a number of different conditions, making measurements and trying to establish that mathematical relationship that involves the rate law, that reaction rate. Just like yesterday, you will follow this up by watching the video on reaction kinetics and construct the overall or differential rate laws for a number of reactions, all followed by a discussion of how these equations are set up. We will end class as normal with you all completing the practice problems and then coming back together for an exit ticket to see what we learned about the mathematical relationship between reaction rates and concentration. This lesson proceeds exactly as the first did. The students are engaged with that simple yet visually arresting iodine clock reaction, and then they follow this up with a simple exploration of that reaction that helps them set up their framework for constructing the differential rate law for that reaction. For the explain step, the students watch a video on differential rate laws and how to construct the integrated rate law graphs based on reaction order, which then the class comes back together and discusses as a whole, again with that teacher-mediated discussion. Students then elaborate on this knowledge with a simple set of practice problems and evaluate it before they end with an exit ticket. I found that following the 5E model was helpful in structuring my ideas for these lessons, and I believe that enacting them would help my students stay engaged and be effective at teaching them reaction kinetics. The resources that I used are broken out by lesson on screen, and those links will take you right to each resource. Finally, here are my literature sources regarding kinetics, mastery style learning, and the 5E instructional model. I hope that this can be as helpful for you as it was for me.